Everyone, my name is Jorge Isaac and my teammate is Isaac Ramirez. Today we are looking at chapter 7. Let's make some noise. In real world applications, optical sensors are never perfect. They suffer from thermal fluctuations and bad lighting, which introduce digital noise. In this chapter, we'll learn how to simulate this noise and how to clean it. So first, we simulate impulse noise, commonly known as salt and pepper. We used a pseudo-random number generator to iterate over the image matrix based on an specific probability. We forcefully overrode individual pixels to either absolute zero, which is black, or 255, which is white. This simulates the earth or saturated pixels on a camera sensor. So let's run it and wait a little bit. As you can see here, this is the result. We can appreciate a lot of particles. This is white, this is black, and so we generate particles, so you can see here, white and black. So let's go to the next one, which is Gauss. Next, we generate statical noise. We created a matrix using a normal Gaussian distribution with a high standard derivation. By algebraically adding this stochastic matrix to our original image, we alter every single pixel slightly. This simulates the uniform static you typically see in low light conditions. So let's stop the case and run it again. You can see here it's more nice. You can see it's like the static from OTBs. That's how we simulate this, and we can increase the number and we can see the difference. For example, if we exaggerate 15, let's see how it works. It's a lot more static on the image, so you can see it looks like an old TV. So let's put it back on 25. So the next, we save this. Okay. We generate a statical noise. So finally, we apply low pass filters to restore the image using spatial convolution. As you can see in the results, the standard average filter plus the image noise. So let's run it. You can see here. It's tight. The Gaussian blur uses a weight kernel. Sorry. Finally, we apply low pass filters to restore the image using spatial convolution. As you can see in the results, the standard average filter blurs the image noise, but it also destroys the sharp edges of the image. The Gaussian blur uses a weight kernel and is highly effective at smoothing out the normal Gaussian static. However, the most impressive result is the median filter because it is a non-linear streaming algorithm. It selects the absolute middle value of the neighboring pixels. This completely eliminates the stream salt and pepper dots while perfectly preserving the sharp structural edges of the original image. Maybe I can show more readily if I sum it. For example, the results you can see more efficiently. So you can see every result is different from the original, the blur, the chaos filter, and the medium uh, filter. So understanding this filter techniques is essential to clean our raw visual data before feeding into any detection algorithm. So let's see a little bit of the chapter 7 with my teammate Isaac Ramirez. Thank you.
7. This chapter is about digital noise. In the real world, cameras are not perfect. Sometimes they take bad pictures with dots of static because the light is bad. First, we wrote a Python code to add fake noise to clean the picture. We added random black and white dots. This is called salt and pepper noise. And also added static like an old television. Second, we learn how to clean the picture. We use special mathematical tools called filters. A filter is like a blur that makes the picture look soft and clean again. We test the three different filters. We start with one filter is very good for cleaning static, another filter is perfect for removing the black and white dots without destroying the picture. In this chapter is very important. We need to clean our images so our camera can see the object clearly. Thank you.